If you've listened to people like Andrej Karpathy over the last really half a decade or more, you've heard people talk about moving from software 1.0 to software 2.0. But what does this actually mean? And more importantly, what are the consequences for both the creator of the software and the user of the software? Well, as it turns out, Demis Hassabis, the founder of DeepMind, actually has some really profound thoughts on this in a recent interview, and I want to use them as a springboard for my own thoughts on the subject. So let's take a look. Hey y'all, it's Dr. Know-It-All. First of all, a very quick thank you to everybody who watched my last video. If you haven't caught it yet, you can check it out up here. It has nothing to do with AI or Tesla or anything. I really appreciate the outpouring of support and the subscribers and everything else. So thank you all so much. I really do appreciate it. It gives me a great deal of encouragement. So without further ado, I want to get to the topic du jour, which is talking about the stochastic nature of software 2.0 and how that's profoundly different than the heuristic nature of software 1.0. So in order to do that, I'm going to start with about a 5-minute clip from a much longer interview between Hannah Fry and Demis Hassabis. Of course, I will leave a link to this in the description so you can watch the whole thing. It's like 52 minutes long. Please do watch it. It is an excellent interview, but I'm just taking a little piece and then I'm going to springboard off of that and talk about my thoughts about the consequences of software 2.0 being stochastic, or in other words, random. Let's take a look at the clip.
There's a lot of learning that is going on, and we're learning fast, which is good because we're at relatively low stakes here with the current technology, right? So it's not that powerful yet, but as it gets more powerful, we have to be more careful. And that's just learning about the product teams that are, in other groups, learning about how to test Gen AI technologies. It's different from a normal piece of technology because it doesn't always do the same thing. It's almost like testing an open world game. It's almost infinite what you can try and do with it. So it's sort of interesting to figure out how do you do the red teaming on it.
So red teaming in this case being where you're competing against yourselves.
Yeah, so red teaming is when you set up a specific separate team from the team that's developed the technology to stress test it and try and break it in any way possible. You actually need to use tools to automate that because nobody can red team. Even if you had thousands of people doing it, that's not enough compared to billions of users. When you put it out there, they're going to try all sorts of things. So it's kind of interesting to take that learning and then improve our processes so that our future launches will be as smooth as possible. And I think we got to do it in stages, where there's an experimental phase, then a kind of, there's closed beta and then launch. A little bit, again, like we used to launch our games back in the day. So you sort of, and learn at each step of the way. So there's, and then the other thing we got to do, I think we need to do more on, is use AI itself to help us internally with red teaming and actually spotting some errors automatically or triaging that, so that then the human, our kind of developers and human testers can actually focus on those hard cases.
You said something really interesting there about how you're just in a much more probabilistic space here, right? And then if there's even a very small chance of something happening, if you have enough tries, eventually something will go wrong. And I guess there have been a couple of mistakes that, public mistakes.
Yeah, so that's why, I think that, as I mentioned, that product teams are just getting used to the sorts of testing. They tested these things, but they have this stochastic nature, probabilistic nature. So, in fact, a lot of cases where, if it was a normal piece of software, you could say, I've tested 99.999% of things. So then it extrapolates. And then it's enough because, there's no way of exposing the flaw that it has, if it has one. But that's not the case with these generative systems. They can do all sorts of things that are a little bit left field or out of the box, out of distribution in a way from what you've seen before. If someone clever or adversarial decides to, it's almost like a hacker, decides to push it in some way. And it could even be, it's so combinatorial. It could even be with all the things that you've happened to have said before to it. And then it's in some kind of peculiar state, which then, or it's got its memories filled up with a particular thing. And then that's why it outputs something. So there's a lot of complexity there. But it's not infinite. So there's ways to deal with it, but it's just a lot more nuanced than launching normal technology.
I remember you saying, I think it was like in the first first time I interviewed you about how actually you have to think that this is a completely different way of computing. You kind of have to move away from the sort of the things that we completely understand, the deterministic stuff, into this much more messy, like probabilistic, error-ridden place, as well as your testers. Do you think the public slightly has to shift its mindset on the type of computing that we're doing now?
Yeah, I think so, because, and maybe that's something we, another thing, interestingly, that we're thinking about is actually putting out a kind of principles document or something before you release something to show what is the expectation from this system. What's it designed for? What's it useful for? What can't it do? I think, there is some sort of education there needed of like, you'll be able to find it useful if you do these things with it, but don't try and use it for these other things because it won't work. And I think that's something that we need to get better at clarifying as a field, and then probably users need to get more experienced on. And actually, it's interesting. This is probably why chatbots themselves came a little bit out of the blue, right? Even obviously ChatGPT, but even to OpenAI, it surprised them. And we had our own chatbots, and Google had theirs. And one of the things is we were looking at them, and we were looking at all the flaws they still had, right? And they still do. And it's like, well, it's getting these things wrong, and it sometimes does, hallucinates and blah, blah, blah. And there's so many things. But then what we didn't realize is actually there's still a lot of very good use cases for that, even now, that people find very valuable, summarizing documents and really long things, or writing, awkward emails or mundane, forms to be filled in. And there's all these use cases which actually people don't mind if there's some small errors, they can fix them easily and saves a huge amount of time. And I guess that was the surprising thing. People discovered when you put it in the hands of everyone, there were actually these valuable use cases, even though the systems were flawed in all of these ways we know.
Okay, so a lot to unpack there. Let's begin with traditional software 1.0. If you're too young or haven't done a lot of programming in your life or anything like that, traditional software is heuristic software, basically. It's you as the originator of the software, or the team of people if it's a large piece of software. You come up with a bunch of rules. So it could be like, if this text string has the word big in it or something like that, then do this. If the text string has the word large in it, do this. Also, if it has the word extra large, whatever. So you can see immediately that doing something heuristically can be very, very precise, because you can search a text string for the word big or large or extra large or something like that. If you define this code precisely enough, it will do exactly what you want. The downside of this is that there's probably, 100 different ways to say something that's big in the real world. So that means that you might have to have 100 different instances of tests just for that one thing. And the likelihood is that you're still going to forget something. So this is what's called heuristic. Heuristic is rule of thumb, basically. It's just like you think about it as a human being and you're like, what would the right answer be? If you're thinking about what does a stop sign look like, you can define things like it's an octagon. It's primarily red in the United States, at least, has white letters on it. They spell STOP. It has a white outline, usually sits up on a pole. You can think about those things, but there's probably other aspects of a stop sign that make it not quite that simple to define. So the advantage of heuristic programming is you know exactly what it's going to do. If you look back through the code, it's like, yep, this is what it's going to do. The disadvantage of it is that reality is messy, and it's really, really hard to get every single possibility if you're dealing with a complicated situation. If you're just trying to do something that's, highly mathematical, like a spreadsheet or something where you're converting something from US dollars to Canadian dollars or something like that, then yeah, heuristics is the way to go. Don't do software 2.0 because it's a simple mathematical conversion. It's multiply one by some number and you get the other thing. No problem at all. You just have to take in whatever that number is every day and you can get the exact conversion. But when you're trying to do something like take natural language, like, hey, make me a program that will do the Fibonacci sequence or something like that, you ask your LLM. That is something that if you're going to do that heuristically, you have to then go in and think about what is a Fibonacci sequence? How would I create it? What sort of errors could arise in that? So you have to do a lot of thinking. There's a lot of mental exercise that a programmer has to do besides just knowing the programming language. So So that's also a basic thing. You have to have a basic skill because a programming language, even something like Python that's very readable, is not English. It's not Japanese. It's not Chinese. It's not any of those languages. It's a very distinct syntax, and you have to be exact. You can never make a mistake or else it blows up and gives you a syntax error. So advantages of software 1.0 or heuristic code is that you know exactly what it's going to do if you look deep enough at it and you're skilled enough, and you as a human being can more or less wrap your mind around it. Although if you get to large projects, it becomes very difficult to do that because many people have worked on it. So that is a little bit of a, it can turn into kind of a black box, even though if you can look into it deep enough, you can eventually figure out what's going on inside the code. When you get to software 2.0, which as Andrej Karpathy has defined it is neural network based, most people think of generative AI when they think about that, but it can also be done in classification and other things like that. But basically what you're doing is you're substituting lines and lines of code that you can read, right? It's all human readable, even though it's, it's a distinct language of its own, but you can read all of that stuff if you have the skill. What you're doing is substituting that for giant, essentially spreadsheets. It's tensors, it's multidimensional spreadsheets of numbers that you're then taking your input, whatever your input is, whether that's pixels of an image or some language that somebody says, I want to get a large Coke or something, right? If you ask that kind of a question, that would also be an input that then goes into your tensors. There's multiplication and addition and all of that stuff that happens. And then out at the other end of that pops something, which is, it could be a classification in the case of a picture, like that's a dog. In the case of a large language model, it might be a response like, hey, we don't serve Cokes here. Would you take a Pepsi or something instead, right? So the answer that pops out is not based on a bunch of rules that you have defined, but more or less a bunch of rules that this neural network has figured out on its own. And the way it figures that out, of course, is that you feed it a whole bunch of data. It trains on that data. You give it reinforcement learning. It figures out how things are going to work. And then it goes in and it adjusts all of those little weights, all of those numbers in that super hyper spreadsheet. It figures out all the little numbers that it needs to adjust. And then it takes the input, it processes it, multiplies those numbers and adds them all up in a specific kind of way, and out comes a response, whatever that response is that you want. So the big advantage of neural network-based software is that it can learn from reality, whether that's language or images or video or audio or things like that. It can actually figure that stuff out on its own. That's very complicated for humans to do. If you try to do this heuristically to define what a stop sign is in every possible condition, and I talk about stop signs a lot because I think about Tesla and their driving software. And back in the early days, 2016, 2017, 2018, when Andrej Karpathy was putting together the original Tesla AI FSD team, they were doing mostly heuristic code. It was like, hey, what if we find this? This might be an edge. This might be a letter. This might be all of these things. So you can imagine hundreds of thousands or millions of lines of code, most of which is just going like, does this look like this? If yes, then do this. If no, then do this. So just if-then statements, out the wazoo over and over and over again. That Andrej Karpathy was very happy about, back in 2020, 2021, 2022, that software 2.0 could eat software 1.0 for these types of use cases, where instead of doing that, you just give it a ton of frames of video and you say, you figure it out. So that's the end-to-end neural network that Tesla has. But that's not just Tesla. That's also large language models and any other kind of AI-based software that we're talking about these days. So it could, again, be categorization or something. It could be generative, where you're getting large language models or producing pictures or whatever the output is that you want. But instead of having this human-defined code, this heuristic code, what you get instead is this data-based code. It's not even really code anymore. It's just numbers. And there's a very small amount of wrapper code that goes around it that defines how you're going to do the multiplication and addition to get the output from the input, matching sizes. I mean, it is messy when you get down to it, but there's very, very little code, which is why in the case of Tesla, for example, you can go from 300,000 lines of code to a neural network that is much, much smaller to do the control systems. And that's what Elon was touting about when we moved from version 11 of full self-driving to version 12 of full self-driving. But going back to the beginning of what Demis Hassabis was talking about, the downside of all of this is a certain level of fragility, and that fragility is tied to the randomness of the output, or as Hannah Fry said, the probabilistic nature, or as you could also call it, the stochastic nature of the output. All of those things are relatively the same thing. So if you get an input like an image of a stop sign, right, you're going to work it through the neural network, and out at the other end, maybe you want it to categorize stop sign or no stop sign, right? That's it's a very simple neural network. It's just like, hey, tell me if there's a stop sign in the picture or not. And what you can do is you can feed many, many many pictures of stop signs into this neural network, and maybe 99 times out of 100, or 999 times out of 1,000, or 9,999 times out of 10,000, it's going to say stop sign in the correct case, and it's going to say no stop sign if there isn't. But that 1 in 10,000 example, it's going to return, yeah, that's a stop sign there, where it's actually not. And the problem is there's almost no way to know when it's going to do that. It's very, very complicated to figure out what instances are going to cause a neural network to fail, but they are fragile. They do tend to be fragile. Back in the old days of neural networks, like 5 or 6 years ago, when we would look at ImageNet and classification and stuff, there is an old hack that you can use, which is basically you can feed a classification network a picture of a dog or something, and it goes dog. And you can sprinkle in a little bit of noise. In other words, random pixels in the image that a human being can't even see. And when you feed it in, it says like giraffe or zebra or something. It freaks out the neural network. They tend to be very, very sensitive to the initial conditions in ways that human beings don't expect. And of course, Demis started off the clip that I showed you by talking about the red team, the people who are supposed to break these systems, and how challenging it is for them to do that, because it's not even just the state of a system like an LLM, it can actually be the history of the LLM as well. So if you've asked it a particular sequence of questions that don't seem to have anything to do with breaking it, when you ask the next question, something that should turn out something basic that it should produces something bizarre and, an unwanted effect and a hallucination or something instead of the proper output that you expected. And of course, as both a creator of software and as a user of software, that can be very, very frustrating. And that's exactly also the reason why if you're driving and you're full self-driving and 999 times your car does a particular sequence of moves exactly right, it gets to this particular light, takes a right-hand turn, but today the sun's in just a particular position and the clouds are just in a certain way, and it freaks out and does something wrong. That's exactly why you can have bizarre behavior in situations where you're like, why am I getting this bizarre behavior? Well, it's because all of this stuff is stochastic. It's all probabilities. It could have a 99.9% chance of doing it right every single time, but there's always that 0.1% chance. And if you drive the car enough or generate enough text output or classify enough images, you're going to find that, 0.1% where it fails. So what are the consequences of this? The consequences is I think we have to reset our expectations somewhat. And I think people have kind of done this to some extent with large language model like ChatGPT or Gemini or something. I think as users, we've kind of started to reset our expectations and understand what we're likely to get out of these systems, both the good and the bad. I mean, fantastic. It can write you an email that you didn't really want to write, and you can just give it a prompt and you can give it the email that you're replying to, and it will do something like that. And it's like fantastic. It'll do that. But what you'll notice is that sometimes it'll have stupid words or it'll make a mistake or something like that. So you still have to go back in and fix it. So you can't assume it's going to be 100% accurate, but it's still a time saver and it's great for that. But Demis here particularly talks about publishing a document with a release of a new piece of software, like basically telling the consumer, this is what you can expect out of this piece of software. Don't expect it to do this. You can probably expect it to do this. It will almost definitely do this. That is probably good to set expectations and have people kind of understand the basics of what they're getting into and what they should be able to expect out of a large language model, out of a large action model, out of full self-driving software, et cetera, et cetera. And so that's the kind of thing from a consumer standpoint that I think would help. The other thing is just to kind of know, to watch this video and try to ingest in your head, this is not heuristic code. This is not something that a programmer can go in and exhaustively say like, if this, then that, if this, then that, if this, then that, right? So there's no way to know exactly what this thing is going to produce every time, and just understand that that's the output you're going to get, and understand that imperfection exists in reality and imperfection will exist in the output, at least for the foreseeable future. I don't know any way to get around this. The way things are going right now. Maybe there's an eventual kind of software breakthrough that will get it to the point where it's basically 100% accurate, but that is not going to happen with the architectures we have right now. And for those of you out there who are creators of software, I would say that you also have to reset your expectations as well. For my case, I'm working on a contract that I can't talk about due to NDA, but as part of that contract, the last week or 10 days of working on this contract, I've been working on going from large language model prompting training and large language model output. So kind of a, strings of text, but fuzzy-ish strings of text, things that are not exact, to I need to go to something that has got to be very, very exact. So I'm having to traverse between the, stochastic probabilistic nature of large language models and the rigid nature of heuristic code, where things have got to be exactly the way they want to be in order to produce the output that's needed. And that is exceptionally frustrating because I'm basically sitting between software 1.0 and software 2.0 and trying to translate between the two of them. And as it turns out, that's extremely complicated and extremely frustrating. So I know firsthand that this is something where you have to kind of reset your expectations. You have to think about ways in your, old software 1.0 code mind of how can you be as robust as possible to get the large language model output and to process it properly. And then on the LLM side of things, you have to think about how you can prompt engineer to get as exact an output as you possibly can so that as you feed it into the software 1.0 sort of stuff, it works as expected. So it's very complicated and you really do have to reset your expectations. Different kind of programming paradigms. Of course, I grew up with software 1.0 because I've been programming since the Stone Ages, but basically that kind of programming is I'm used to it. It's cool. I like doing it. That's in my wheelhouse, but doing prompt engineering programming, which is basically what I'm doing on the front end of it to get the large language model to produce the expected outcome, is very different and very frustrating because I'm like, yeah, this works. And then I try just the slightest alteration to the input and the whole thing breaks. So it's very frustrating to have stuff like that going on, to have that brittleness happen with software 2.0, but it is something that over time I've figured out how to kind of blend the two of these things. So anyway, the big picture takeaway for creators is that you really have to reset expectations too as you create this code. You can't expect it to behave 100% the way that you want it to. It's going to throw you weird errors as you use it, and you just have to figure out ways of prompting things differently or fine-tuning things differently or reinforcement learning, adjusting things as you need to. Any of those techniques are perfectly reasonable to try to use to get the software to produce what you expect most of the time. But as Demis and Hannah talked about, this is probabilistic. It's not going to produce the output you expect all the time. So both for users and for creators, you have to kind of reset expectations. And I think that the sooner we do that, the happier people are going to be both creating this software and utilizing this software, just knowing that it's going to work most of the time, and hopefully very, very most of the time, but sometimes it is going to glitch out and you're going to get bizarre behavior because this is not deterministic. This is not adding 1 + 1. It's more like flipping a coin 1,000 times. Yeah, it's probably going to come out close to 500 heads and tails, but once in a while, if you flip it 1,000 times, it might be 550 to 450. So, you can get big variations once in a while. Most of the time it'll turn out the way you expect, but sometimes it's going to turn out bizarrely. All right, thank you for coming along with me on this geeky little deep dive into software 1.0 versus software 2.0. I hope that thinking about this in a little more detail, even if you're just a user of the software and you never actually intend to create it and you haven't programmed in your life or anything, I hope that it helps you to understand and set expectations about what you can really figure that this software 2.0, generally in the form of large language models or image creators or things like that, that's how most users use this kind of stuff these days, but also in the form of full self-driving, if you use Tesla's full self-driving, just to understand and to set your expectations about the nature of this software and why it's going to fail sometimes. And the fact is there's no way to avoid that, at least in the near term, until and unless we get a software architecture breakthrough that really, really changes things. In the meantime, enjoy the stochastic nature of reality. That's just the way things are. And take advantage of the massive software improvements that software 2.0 brings us. Please let me know in the comments what you think about all of this stuff, especially if you're a software creator. I would love to hear how you think about software 1.0 versus 2.0, how you program for software 2.0, all of that kind of stuff. And if you're a user, let me know as well the frustrations that you've had with using something like ChatGPT or an image generator or anything along those lines. While you're down there, if you don't mind liking and subscribing, that super helps out the channel. Thank you so much, and I will see you in the next video. Bye-bye.